So in this particular class, we shall be continuing where we left the previous day. That is, we are going to cover the remaining continuous distributions. So starting with, we would be starting with normal distribution, which is fundamentally one of the most important distributions in statistics. So give the heading normal distribution. Give the heading normal distribution. So under it, first of all, write in the first point, it is also known as Gaussian distribution. It is also known as Gaussian distribution. Before getting into the specific form, given the fundamental importance of this distribution, we would be taking a highlight of certain pointers as well, be it with respect to where exactly this is applied, what few properties it possesses, and so on. Let me share my screen. So under normal distribution, rather I'll dictate itself. So you all take down the notes. First point, this distribution has a symmetrical, this distribution has a symmetrical bell-shaped, B-E-L-L shaped, bell-shaped, within quotes, density curve. By density curve, what I mean is basically the PDF. Next point, it is a good model. It is a good model for the distribution of measurements, that occur in practice, in a wide variety of different situations. In a wide variety of different situations. For example, height, weight, IQ score, or exam score, Next point, it provides good approximations. To various other distributions. Give a dash and write. In particular, it is a limiting form. Of the binomial distribution. Next point, it provides a model. For the sampling distributions, of various statistics. Next point, much of large sample statistical inference is based on it. And some procedures require an assumption that a variable is normally distributed. That a variable is normally distributed. Next point, it is a building block. It is a building block within quotes for many other distributions. This was just to give some background. Now, slowly and steadily, let's take a look at the various components. To begin with, the representation. X follows normal, just an n, mu, comma, sigma square. We have two parameters, one is mu, the other is sigma square, and these are nothing but the mean and the variance of X as well. So the PDF is given by 1 by sigma, might look a bit complex to begin with, 1 by sigma root 2 pi exponential minus half x minus mu by sigma whole square, and the range is from minus infinite to plus infinite. Keep in mind, mu can take any value, positive or negative. Sigma square has to be positive. I mean, sigma square, or more technically, sigma needs to be positive. So sigma, you can write it down, must be positive. Mu can take any value. In doubt? Okay. So as for CDF, we do not have a closed form. We do not have a closed form for a normal distribution. Next, expectation is nothing but mu. Variance is nothing but sigma square, and the skewness is nothing but 0. We will not attempt right now to derive the mean or its variance from first principles. We can take these results as it is. Again, using various other techniques which we are going to cover in the following chapters, we can see that there is something called a generating function, moment generating function. Using that, we can find the mean, variance, skewness directly as well. So we would be doing that for a lot of distributions going forward. So yes, these are the properties. Now, next coming to it, how the graph structure looks like. I mean, on the y-axis, we basically have nothing but the PDF itself, and on the x-axis, we have nothing but the values which x can take. Note that negative values are allowed. So maybe I can draw a graph in this form. This is fx. That's why the name symmetric bell-shaped curve. If you look at this, looking nothing but in the form of a bell only. Just something on a lighter note, if you're not aware of distribution of anything, ultimately we can approximate everything to follow a normal distribution. Later on, we'll see whenever we have no data regarding the exact form of a particular random variable, we can approximate it to be nothing but coming from a normal distribution. And the reason is that a lot of things which we see in nature when we try to measure, or a lot of data which we observe, tends to be in the form of normal distribution. So the closest distribution, or the one which is observed in a lot of things, would be nothing but the normal distribution. So these are the properties. Now, unlike other distributions, let's say whatever distributions I've covered so far, be it discrete, be it continuous, wherever you will see the parameters which we have are involved in both mean as well as the variance. Normal distribution is one of those few distributions, or in fact, probably the only one which we are covering in our syllabus, where the mean parameter and the variance parameter are completely independent of each other. That is, we have two parameters, mu and sigma square. Mean does not have any sigma square term, variance does not have any mu term. If you will take a look at any other distribution which we have covered so far, there would be some relation between the mean and the variance. So later on, again, we are going to use this property that for a normal distribution, its mean and its variance are independent with respect to each other. So this is normal distribution. A special case is the standard normal distribution. So give the heading standard normal distribution. If mu is equal to 0 and sigma is equal to 1. If mu is equal to 0 and sigma equal to 1, then we have a standard normal distribution. And the usual way to denote it is, keep this in mind, Z. A lot of times when you will see we have a Z random variable, so on, if nothing else is mentioned, by definition, Z is nothing but used to represent a standard normal distribution where the mean is 0 and the variance is 1. And if we'll again take a look at the PDF, this will reduce to 1 by root 2 pi e to the power minus z square by 2. You can substitute sigma as 1, mu as 0, and the PDF will be reduced to this form. Now, a lot of things we are gonna study. It might take us some time just to recall all this. So as you keep on practicing, a lot of notations will be clearer to you, and you will not have to give separate effort as such to memorize it. By virtue of practice, you will end up kind of having this at the back of your mind itself. So for a standard normal distribution, we have a specific notation for the PDF. This is the usual way to denote the PDF. Phi x. This is nothing but the PDF of a standard normal distribution. A specific way to denote the PDF is nothing but phi x. Note that inside, whether you write x, a, b, c, d, s, all are the same thing. This is nothing but a dummy variable. Here I have written fz. So it is coming in the form of z. I could have also written fx, and instead of z, I would have had x over here. So don't get confused with this. Normal ways to write x. When we perform integrations, we sometimes write s, sometimes we write t, so on. So don't get confused. This is nothing but a dummy variable. So phi x is PDF of nothing but a standard normal and capital phi. This is the way to write capital phi. This is nothing but CDF of a standard normal distribution. That is, this is nothing but probability Z less than equal to X. So now, again, we saw that there is no closed form for CDF as such. If you would remember yesterday in the last class when we were covering chi-square distribution, we saw something as the probability tables, right? Similarly, we have such a table for the standard normal distribution as well. So whenever we want to compute certain probabilities for a normal distribution, we'll have to ultimately convert it into first a standard normal distribution. We will shortly see how we do that. And we have the respective probabilities for a standard normal distribution. So these are the usual notations. Now mean obviously it's 0. Remember that this is nothing but a symmetrical distribution. Therefore the mean, median, mode all are nothing but equal to mu. In case here it is nothing but equal to 0. So the graph will look something like this. The graph for the PDF of a standard normal distribution will look something like this. Again, it's not pretty much well drawn. Let me give it another shot. Now there are certain properties which we would be required. Okay. So first of all, if we take a look at the graph, let me draw another graph over here to get the properties. And note that these are true for right now I'm talking about. Okay, just a second. Hmm. So this is the PDF now, standard normal for a standard normal distribution. The area, let's say this is the point A, the area which is towards the right of A is nothing but equal to the area which is towards the left of minus A. The distribution is symmetric in nature. That is, you take any point A, the area, and assuming A is positive, the area which is towards the right of A is nothing but equal to the area which is towards the left of minus A. Now, how we use this is we have been given, we will be later on looking at the actuarial tables. These values are available only when Z is positive. These values are available in actuarial tables only when Z is positive. So what do we need to do in case Z is negative? So we would be using the following cases. See, you need this probability. Probability Z less than minus A. Probability Z less than minus A. Take a look at the graph. This is nothing but this particular region which we are looking at. This is nothing but probability Z greater than A. And I am assuming A right now to be positive all along. And this I can compute as 1 minus probability Z less than A. Again, equal to sign you might or you might not give. It's a continuous distribution. Doesn't really matter as such. So my focus is if you want to compute this sort of probability, it's not directly available in actuarial tables, but you can compute in the form of 1 minus 5A. So this is the first result. Take a look at the second one as well. Say I want probability Z greater than minus A, which is nothing but which region? This entire region. Right. By symmetricity, I can say probability Z greater than minus A will be nothing but probability. This region will be nothing but equal to this region. Or alternatively, if not resonating to you clearly, can I write probability z greater than minus a is nothing but 1 minus probability z less than minus a, and z less than excuse me, minus a is nothing but and we get the result. So this is just to show you all in case you need to find any sort of probabilities when we have a negative number to be given for a standard normal distribution, how to modify it so that we can take the help of actuarial tables. So do take this down. Another thing, if you will take a look at the PDF is symmetrical, right? That is the height of the function at this point is nothing but equal to the height of the function at this particular point. Since the PDF is symmetrical in nature, if I look at the height of the function at point A, this will be nothing but equal to the height of the function at point minus A. Mathematically speaking, whether I take the value z or minus z, PDF remains same only. So from this, another result which you can use is, note that these were for calculation of probabilities. You could also note this down. Phi z is nothing but equal to phi minus z. And along with this, few very basic property. If I write phi of minus infinite, capital phi, this is nothing but probability z less than minus infinite. Is there any value left of minus infinite? No. This is nothing but 0. Similarly, phi is 0. 0 is nothing but the median. So this will be half. And phi infinite, probability z is less than equal to infinite. It covers the entire area. So this must be nothing but 1. I can take this down as well. Some of the properties we are dealing with, you might not directly require in your CS1, but in higher papers, be it CS2, CM2, or even other higher SP papers, say it might be that certain of these properties would be required. See, whenever you try to pick up a data set from real life and try to model it, you need to understand first of all the specific, let's say, features of the data set and the available distributions which we have. What are the features of those distributions as well? Then only will we be able to come up with a, let's say, initial guess of which distribution might be appropriate to model a particular data set. Numeric calculation wise, derivation wise, these would be fairly straightforward. What we'll need to focus in certain of the key features, like here the first key feature which I mentioned was it is symmetric in nature. Second, which I mentioned was, which is very peculiar to this distribution, is that its mean and its variance are independent in nature, and this is a very powerful property which has a lot of further applications. Next, what we're looking at is because it is symmetric in nature, all these properties will follow accordingly. That is, the area towards the right of A will be nothing but the area which is equal to the left of minus A, and so on. Yes, Harsh, CDF of infinite is 1. What does CDF of infinite mean? Probability X takes a value which is less than equal to infinite. So the set of possible values is what? Minus infinite to infinite. When I want to calculate the probability that a random variable takes a value which is less than infinite, by definition, that is always going to be 1 only, because there is no value possible towards the right of infinity as such. Infinity by definition is the right extreme, the highest possible value which a random variable can take. Now, along with this only, I might just add. So what I'm trying to say is in tables, what we have is simply probability z less than equal to a. I have computed this form z less than minus a, z greater than minus a, and the third one could be probability z greater than a, which will be straightforward, nothing but 1 minus probability z less than a. So we have four probabilities, either z can be greater than a, less than a, greater than minus a, or less than minus a. Less than a directly available in tables. For all other three cases, this is the formula to be used. Again, you shouldn't memorize it in the form, this should naturally come to you. Back of the mind, you should remember the result, but the derivation, if you want to say, is fairly straightforward. Now let us look at certain more properties. Again, just keep in mind the properties which I'm mentioning right now might not be directly relevant for CS1 as such, but for completeness of normal distribution, we are doing it. This is the point 0, this is point 1, this is point 2, say this is point 3, minus 1, minus 2, minus 3. Now, approximately 34% values reside in the interval 0 to 1. Approximately 14% values lie in the interval 1 to 2. And approximately 2% of the values lie in the interval 2 to 3. Again, I'm saying approximate. You might see these add up to give us nothing but 50%. Similarly, from minus 1 to 0, it's 34%. This is 14%. And this is 2%. So you might think all 100% is coming between minus 3 to 3 only. That is not the case. That is why I'm saying these are approximate values. Point is, a bulk of the values lies between minus 3 and plus 3. The probability of a standard normal variable taking a value between minus 3 to 3 is almost 1. Not exactly 1, but it is almost 1. That is, any values which are in excess of magnitude of 3, be it in either direction, is highly unlikely. Is going to be highly unlikely. So, if you go through certain, let's say, business news articles, or if you would have come across certain business news channels wherein they quote that the markets are currently trading 1 standard deviation above mean, 3 standard deviations above mean, so on. So, point is, a lot of them assume that the returns are, let's say, normally distributed. So the probability of having anything which are more than or less than 3 standard deviations is extremely low. If you will clearly take a look, mean is 0. What is my variance or standard deviation? 1. So the points 3 and minus 3 nothing but corresponds to what? 3 standard deviations away from the mean. 3 standard deviations away from the mean. So the probability that a normal random variable takes a value which is away 3 standard deviations from mean is extremely less. So you all can take this down again. Do mention these are approximate values. Next, you all could also take this point. 50% of the values, 50% of the values. When I'm saying 50% of values, see what I'm trying to say is, if this is the area under graph, 30%, 34% of the area lies between 0 to 1. So when I say 50% of values, you can also think that the 50% of area under graph. So the next statement is 50% of the values lies in the interval, minus 2 by 3 and 2 by 3 for a standard normal distribution. Again, all these are for standard normal only, for a standard normal distribution. Now, the property to begin with, if X is a normal distribution with parameters say mu, comma, sigma square, and if I define a random variable Y to be nothing but ax plus b, then y is also nothing but a normal distribution. That is, you make any sort of manipulation, any sort of linear adjustment to a normal distribution, any sort of linear adjustment to a normal distribution, the resulting distribution is also going to be normal in nature. If x follows normal mu comma sigma square, y will follow normal a mu plus b comma a square sigma square. We can directly use the results which we had studied in the class random variable. If y is ax plus b, what will be expectation y? A and b are constants, so a into expectation x plus b. What is expectation x? Mu. So what is expectation y? A mu plus b, which becomes my parameter. Remember that for a normal distribution, the parameters are nothing but the mean and variance itself. If I want variance y will be nothing but a square variance x. So a square sigma square, and we get this result. So this is the first one. I'll give you time to note it down. Second one, uh, if x follows this, this is the first point. Second point is x minus mu by sigma follows nothing but standard normal. You all can now try to find expectation of this. Expectation of x minus mu by sigma, which is nothing but expectation x minus mu whole divided by sigma. Expectation x is nothing but mu. So mean is coming out to be nothing but 0. Variance. This will be nothing but 1 by sigma square. Variance of x will be nothing but 1 by sigma square into sigma square, which is nothing but 1. So clearly the mean of this is 0. The variance of this is 1, which is nothing but corresponding to a standard normal distribution. So the line which I mean in words is any linear modification of a normal random variable leads to another normal random variable. Obviously parameters will be adjusted for, but the resulting would also be a normal random variable. So take this down. Now let us attempt to find a few probabilities for normal distribution. And or before going that, let us take a look at the actuarial tables. So here, first of all, we have the parameters are given. We have the PDF, we have the mean, we also have the variance. Next, go directly to page 160. And you will see that we have the probabilities for the standard normal distribution, starting with x with 0. And obviously, the value should be nothing but 0.5 only. because 0 is nothing but the median of a standard normal distribution. So you will see all these values are in increments of 0.01. Starting from 1, we have in this page till 2. If you go towards the next page, we have the value still around 4.4. And if we'll just take a look at the value at 3, if we take a look at the value at 3.99865, matlab what is this? This is the probability that Z takes a value which is less than 3, which is what? Around 99.865%. 99.865%. And obviously this also includes the area what? Between -3 to -infinite. Even if you ignore that, you will see that almost 99.8% of the values lies between the interval -3 and +3. Almost 99.8% of the values lies between -3 and +3. That is the bulk of the values should be within this particular range only. So these are given. Next, you will also see percentage points for the standard normal distribution. We will see later, what do we mean by percentage point. We have two tables actually. One is the probability values and another is the percentage point. Let me explain it to you right now itself. What percentage point gives us is the point. It gives a point and the probability above that point. So for example, let us try to understand or read this value 50%. We need the value probability of having when I say 50% percentile, it means what is the value? The probability of having greater than which should be 50%. So how you could read out this is in this way. Again, this is something we would be covering in far greater detail later as well. See, there are two components. Probability x greater than a equal to b. If we know the value of b, then the percentage point is used to get the value of a. So if b is 50%, I can correspondingly find the value of a. If b is say 30%, correspondingly I can find the value of a. So percentage point is used as the name suggests. Percentage point, probability is given. I need to find the corresponding point in the distribution. Probability tables are used for this way. Let's say I have something of this format. You will be knowing the value of C. You need to find the value of D. So note that for normal distribution, you have both of these. You can use either of them. Even for chi-square, you will be having both of them, percentage point as well as probability value. For some distributions like F distribution, which we would be shortly studying, we just have a percentage point distribution. So even if you want to calculate the probabilities, you have to use the percentage point distribution only. And later on throughout the course, we will see how to use these tables to effectively calculate the values. So now you can take a look. Let's say the 5% percentage point is 1.6449. Then you can look at 2.5%, which is coming out to be 1.96. And then you might also wish to take a look at the 1% value, which is coming out to be nothing but 2.3263. So this is the actual table which you need to refer. Now another thing which you need to keep in mind is for a normal distribution. Let's say this is the point mu. I will plot 3 points: mu plus sigma, mu plus 2 sigma, mu plus 3 sigma, mu minus sigma. Again, the graph, do not scale it. It's not drawn in a very proper scale wise. These are the points which I have plotted. The area between these two is nothing but 34%, 14%, 2%, 34%, 4%, 2%. If you put mu 0 and sigma 1, this nothing but simplifies to what we had drawn for a standard normal distribution. So this is the statement I was making. The probabilities of getting a value which is 3 standard deviations away from the mean is extremely unlikely. And if you will see between one standard deviation, there is almost how much value? 68% value. Between mu minus sigma to mu plus sigma, we have 68% value. So draw this graph as well. Let us solve one question. Again, I'm solving very few questions right now, just the ones which are helping us to understand a particular result. We are solving that only in this particular lecture. In a separate session, focus would be given on the various numericals as well. So say x follows normal 25, 36, and I want to calculate this probability. Probability mod of x minus 25 is less than 4. Now, first of all, if you remember, what does the modulus function do? It gives us the positive value only. So I want mod x to be less than a. When does this happen? When the value will be lying between minus a and plus a. So this I can write as probability minus 4 less than x minus 25 less than 4. X minus 25, well and good. That is what we're actually looking for. When we try to standardize it, I will divide both the sides by 6. I will divide both the sides by 6. 36 is nothing but sigma square. So what is sigma? Sigma is 6. Minus 4 by 6 less than x minus 25 by 6 less than 4 by 6. This comes out to be nothing but minus 2 by 3 less than z less than 2 by 3. And we did, the answer of this should be close to 50%. We actually wrote that the 50% of the values lies between minus 2 by 3 to 2 by 3. But you can't use that result here as such. My purpose is to show how to go about calculating from the actual tables. Now minus 2 by 3 you need to convert into decimal form. Now this 2 by 3, this will keep on recurring. Ideally keep it till 4 decimal places. So it will be minus 0.6667 less than z less than 0.6667. If you're running short on time, if you're running extremely short on time, you might round it off to 2 decimal places, because then directly you will get the value from tables. In tables, all of them are rounded on to be 2 decimal places. If you're taking 4 decimal places, you'll have to perform interpolation. Ideally 4 decimal places, and right now specifically, the ones who would be appearing from IFOA, you are allowed to use Excel or all these things to perform such calculations. So you do not even have to refer to actual tables. You can directly find the exact value from either Microsoft Excel or using R programming itself. So this now I can write as probability z less than 0.6667 minus probability z less than minus 0.6667. This directly I can write in this form. And if you'll remember the result, probability z less than minus a was nothing but 1 minus probability z less than a. So this will be minus of 1 minus 5, 0.6667. And this will simplify to give 25.6667 minus 1. Now, how do you go about calculating this value? You will have the value of 5.66. You will have the value of 5.67. You need to interpolate between these two. And for the time being, let's say if I rounded off this to 2 decimal places, check the value at 0.67. What is the value at 0.67? 0.44. नहीं. Probability refer to the value when x takes the value 0.67. When x takes 0.7485. 857. This I will multiply by 2 and I will subtract by 1, and the answer which I'll get over here is 0.49714. 0.49714, which is very close to 50%. That is what we kind of expected to be. Now, if you take this to be 0.667, then the answer which you will get will be further close to 50%. Because when I quoted, I said between minus 2 by 3 and 2 by 3. 0.67 is not 2 by 3. So if I take 0.667, this also is not 2 by 3, but this is more close to 2 by 3. So remember that statement which I made or mention, कि 50% of the value lies between minus 2 by 3 to 2 by 3. Don't use it for purpose of calculation of probabilities. For that, always refer to actuarial tables. Alternatively, you could take help of R programming or Microsoft Excel to calculate these. Ones who have studied CM1, you all had a class in Excel, right? For statistics part, where we were calculating certain probabilities. In Excel, class 3, statistics, standard normal, binomial Poisson. Didn't do. Chalo, it wasn't required in CM1 as such. Okay. Point is, you can take the help of Microsoft Excel as well to compute all these statistical probabilities. So this is all we have under normal distribution. Next, we would be looking at something called a log normal distribution. And before going into log normal, just take down one property as well. If Z follows standard normal, again going forward, whenever I say Z follows standard normal, in your notebook you can directly write as in this format. You can directly write in this format. Then Z square follows chi-square 1 distribution. Then Z square follows chi-square 1 distribution. So this is another relation between my how can we get chi-square distribution? Last day we saw that we can get a chi-square distribution using a gamma distribution. Today we are using a standard normal distribution. Next, give the heading log normal distribution. Say if x is following normal mu comma sigma square, then the random variable e to the power x, is following log normal distribution with parameters mu and sigma square. So let me define y as e to the power x. Then the way I write it is y follows log normal. Again, here it's written, log. By that we mean the natural log only. It's e to the power raised x. So in theory, completely, we keep on writing either log or ln. Both mean same thing. But when you're using calculator, keep in mind in there log means base of 10. Here by default we're assuming base of e only everywhere. So y follows log normal with parameters mu comma sigma square. PDF again will be something of this form: 1 by sigma y root 2 pi exponential minus half ln y minus mu by sigma whole square. Let me share it with you all in tables itself. Now note the parameters of log normal are also mu and sigma square, but these are not its mean and variance. For a normal distribution, the parameters were its mean and variance. For a log normal distribution, the mean is given to be expectation x is e to the power mu plus half sigma square, and variance is e to the power 2 mu plus sigma square, which if you'll just closely notice is nothing but the square of mean. This term e to the power 2 mu plus sigma square, this is nothing but square of this term into e to the power sigma square minus 1. So whenever you are given ki the say a random variable follows a log normal distribution with mean this and variance this, find the parameters. So what you have been given is mean this value and variance this value. Using this, you need to find, let's say, mu and sigma square. So don't get confused. In normal distribution, mu was mean, sigma square was variance. In log normal, that is not the case. And the log normal distribution is a positively skewed distribution. Normal was symmetric, log normal is a positively skewed distribution. Again, you can also write for CDF, we do not have a closed form. We do not have a closed form. Now, a very important property. If we again want to calculate certain probabilities with respect to log normal distribution, the term which I want to use is standardize. What do I mean by standardize? Try to bring everything to a standard normal distribution. So if y follows a log normal distribution, then log y follows a normal distribution. If y follows log normal, then log y follows nothing but normal mu comma sigma square. This is first result. Second, from here, log y minus mu by sigma will follow standard normal. We did that if a particular random variable follows normal mu comma sigma square, then that random variable minus mu whole divided by sigma follows standard normal distribution. So this is the first result, converting from a log normal to a normal, and this is standardizing it. So whenever you need to compute the probabilities, you need to standardize it. If y follows log normal, you need to bring in the term log y minus mu by sigma. Again, in today's session, the focus remains on the underlying distributions, not with respect to calculations and all. That is something would be done separately. Next, give the heading T distribution. T distribution, small t. Right now, if x, capital X, has a chi-square n distribution, has a chi-square n distribution, and z, capital Z, has a standard normal distribution, can directly write z follows normal 0, 1, and x and z are independent, and x and z are independent, then the quantity z divided by root under x by n follows a Tn distribution. So keep in mind three things. One, we have a standard normal, then we have a chi-square, and both of them are independent. Then this particular quantity is said to but follow nothing but a Tn distribution, where n is nothing but the parameter. And you can write parameter, with parameter within brackets, degrees of freedom, degrees of freedom, brackets close, small n, small n. That is the term z divided by root over x by n follows a t distribution with n degrees of freedom. First point, right? These are certain properties as n tends towards infinite, Tn tends towards a standard normal. That is the limiting case when n tends towards infinite. The limiting case, what we have is nothing but a standard normal distribution only. T infinite is nothing but a standard normal distribution. Next point, it is the T distribution is symmetrical about 0. The T distribution is symmetrical about 0. Let's take a look at actuarial tables again. So on page number 163, if I recall correctly, yes. If you will note that for a T distribution, what we have is the percentage points. So we need to use these only to calculate the probabilities. And later on, we will see how to go about using percentage points for calculating probabilities as well. Just keep one thing in mind. If you take a look at the graph, this is the highlighted area which they have represented as P, and X is the area that is the right of which the area is nothing but P. So from this also you can understand what quantities exactly they are giving us. So whenever you need to calculate probabilities for a T distribution, you need to use basically page number 163. Last distribution, F distribution, capital F. Write down, if two independent random variables have a chi-square distribution, with n1 and n2 degrees of freedom, with n1, write it in this way, n1 and n2 degrees of freedom respectively, then x by n1 divided by y by n2 follows F distribution with parameter n1 comma n2. The quantity x by n1 whole divided by y by n2 follows F distribution with parameters n1 and n2. Now if you closely take a look, can I write also this way, y by n2 by x by n1, both are of similar structure only. This should follow F n2 comma n1. So from here what I can write is F a comma b is nothing but 1 divided by F b comma a. Can take this down. Later on we would be using this result for computation of probabilities. Now note that again for F distribution we only have percentage points table, and more specifically we have just 1%, 2.5%, 5% and 10%. So for T, if you will see, we have 40, 30, 25, 20, 15, 10, 5, so on. But for F distribution, we will see that we have it for 10%, we have it for 5%, 2.5%, and 1%. So using this only, we need to basically calculate whatever relevant probabilities we are required to calculate. So, and we will look at ways. Everywhere we need to finally perform interpolation only. So we'll see how to go about it. So this was regarding all the standard distributions which we require, say it in CS1 or even in papers like CS2 or CM2. Apart from that, another result is given in tables, page numbers 18 if I'm not wrong. Yes, this is very important. More specifically for higher papers, CS2 and CM2, but in CS1 also this can be tested. Page number 18, truncated movements section. There are two results which you can directly use. See, for a normal distribution, they have given that integral x fx dx within limits L to U follows the particular expression where they have defined what is L dash, what is U dash. Keep in mind the first term, this is nothing but CDF, and this one is nothing but the PDF of a standard normal distribution. So this is one result. Similarly, we have it for log normal, which is extensively applied whether we are studying in CS2 or CM2. Integral L to U x to the power k fx dx, a more general form. For normal, we had it only for integral x fx dx. Here we have it for x to the power k fx dx, which is e to the power k mu plus half k squared sigma square phi uk minus phi lk, and they have given the definition of lk and uk as well. So using this, what do I mean by truncated movement? If you will remember, what were moments? Expectation x to the power n, which is integral x to the power n fx dx in its entire limit. When we are not taking the entire limit, we are taking any limit from say L to U. Okay, any sort of limit which is not covering the entire limit, the term which we use is truncated movements. By truncate means we are kind of cutting off, we are reducing the size. So if the original limits for log normal was 0 to infinite, any integral which is not of the form 0 to infinite, say it is either 0 to 100 or 1000 to infinite, these are nothing but examples of truncated movements of log normal. Similarly, for normal, the limits should ideally be minus infinite to plus infinite. If the limits are say minus infinite to 1 or say 0 to infinite, all of these will be falling under nothing but truncated movements. So just take down this in your notebook itself. Results for truncated movements, results for truncated movements for normal and log normal distribution are given in page 18, of actuarial tables. Derivation of this is actually not there in CS1, although you could perform it, but in CS2 we will see we have explicit derivations for same. You all could give it a shot as to how to perform derivation for same, but as such it's not directly required in CS1. So this is under all distributions. Final topic which we have is something called Monte Carlo simulation. Note that this has nothing to do with the brand Monte Carlo, which probably sells, I guess, garments and all, something like that. This is completely different. Now, simulation is a very extremely important topic. A lot of you might not know what simulation is. Once you'll start, let's say, studying for paper, we will realize. Just to give you a background, if I want to generate certain random samples, let's say there's a distribution, I want to generate some random numbers from that distribution, some random values. So this technique of generating certain random values from a distribution is called simulation. Okay. Now there are different techniques to do it. Initially, there was a lot more methods covered. Right now, we just have one method covered, which is the inverse transformation method. It's a fairly straightforward method. As for the, let's say, examination point of view, what you need to do over here is basically you will be given a particular random number either in examination or in actual tables. If you'll take a look at the last page of actual tables, take a look at the last page of actual tables one, certain random numbers are given, pseudo random values from uniform 0 comma 1. So these are nothing but random values. So these are there in tables. You can calculate, you can get them using calculator, you can get them using Microsoft Excel. You can also be provided in the examination itself. So these are certain random numbers coming from uniform 0 comma 1 distribution. Using these, we will generate some random values from any distribution X. It can follow normal, it can follow log normal, gamma, Poisson binomial, any distribution. So my task is to generate some random values. Now you can say I can generate, through my mind only. Let's say if I talk about normal distribution, random values are 50, 100, 200, 300, 400, so on. But there will be some sort of biasness if I generate values in this way. A more better way is you generate a random number systematically. This can be done either through the help of certain softwares, or it can also be done by conducting certain experiments in nature. Like for example, if I kind of toss a coin, if I get a head, I will say the number generated is 5. If I get a tail, the number generated is say 2. This is one natural process. Artificial process or non-natural process is kind of using softwares to generate some random numbers, and these random numbers will be between generally 0 to 1. Using this, we can generate any random number from any distribution, and we will shortly see the technique for same. So initially there were various techniques in CT3, which was the old paper under the prior 2019 curriculum. We had inverse transform method only in CT3. The paper CT6 had certain other techniques. That is something which is not part of current syllabus in any of the actual papers. So right now we would be restricting to a single method only. Give the heading inverse transform method. Inverse transform method. Now the steps are something which are directly there in the material itself. Let us take a look at it. Approach finally application is very simple. What you need to do it at a very simplistic level is equate U to Fx. X is the distribution from which I want to generate certain random samples. There is a result that whatever distribution be X, whatever be the distribution of X, Fx follows a uniform distribution. You all can quote this, take this result. If Fx is CDF of any random variable X, then Fx follows a uniform 0, 1 distribution. We will attempt to take a look at the result of this as well. We'll attempt to take a look at how to derive this. We'll do it separately when we are solving questions. Right now I can take this result. So now our task is U is equal to Fx. So what you would be given with is the value of U. I need to equate this to Fx, and using this I need to find the value of X. So fairly straightforward, right? This I can do when take U is equal to Fx. So for example, if X follows exponential lambda distribution, I know that Fx is nothing but, capital Fx. If you would remember from the previous class, 1 minus e to the power minus lambda x. I will equate this to u. So my e to the power minus lambda x will be 1 minus u, or my x will be minus ln of 1 minus u by lambda. So lambda you will be knowing, you will have the values of u. Using that I can find the value of x. So if there are 3 values of u, I can get 3 values of x. Okay. Alternatively, at times we can also equate u as 1 minus fx. Stick to this only. This I am just saying alternate ways you equate u as 1 minus fx, and then you can find the value of x. Obviously note that you will be getting a different value of x if you use this formula. Point is both of them are correct only, but stick to using this one only. So if I take a look from the material itself, they have written the algorithm over here. The following two-step algorithm is used to generate random variate x from a continuous distribution with CDF fx. Generate a random number u from uniform 0, 1. This would be given in examination. Return x equal to f inverse u. If u was fx, then x can be written as f inverse u. And you might ask why they have written in the form of return. When you're coding, then this is the sort of syntax which you use. Return means this is the value you should be giving out as the output. This is for a continuous distribution, fairly straightforward. Find fx equal to 0. From the graph, see how we can take a look at it. If we are plotting a graph, on the x-axis we have x, on the y-axis we have fx. So if the value of, let's say, u is given, right? If u is given, what I need to do is I need to equate u to the fx. This is the point on fx. Correspondingly, I need to find the value of x over here. So effectively, what I'm trying to do is I am trying to generate a random value for fx. Using that value, I am trying to find the corresponding value of x. And in this way, I will be able to generate some random numbers from the random variable x, which can be positive, negative, anything. If a random variable can take only positive value, so obviously all the generated numbers should be positive only. Capital F, Harsh, u is equal to 1 minus capital Fx. Had I written small fx? Capital F. Everywhere it's capital F, not small f. So this section again is directly from material. As for the discrete one also, let us take a look at. This was for continuous distribution. For discrete one, this is the formula. Now take a look. First, generate a random number u from uniform 0, 1. Next is find the positive integer I such that fxi minus 1 strictly less than nu, less than equal to fxi. Return x equal to xi. We will see through a numerical example exactly how do we need to proceed it. So let us talk about this example. Simulate two random values from Poisson 2 distribution using the random values 0.721 and 0.128. So first what I need to do is calculate the probabilities at 0.0, 1, 2, so on. It is a Poisson 2 distribution. Probability x equal to 0 is this, therefore f0 is this. You can use directly actuarial tables also. We saw that we have the CDF there, right? So this is the f0, f1, f2, f3, so on. What was my first value? 0.721. 0.721 is lying between what? f2 and f3. Therefore, my simulated value is 3. Whichever value u lies between, it's the higher value which I take. And you can see this through the graph as well, why this makes sense. So this will be 3. Now next one is 0.128. 0.128 lies between what? It is less than f0. So my answer will be 0. It is f0, so my answer is going to be 0. Clear? So the way to do it, let's say for this particular distribution, well, if there is any other example, let us take this example, yes. Generate 3 random values from binomial 4, 0.6 distribution using these 3 values. Now again, you can find CDF directly from tables itself, or alternatively calculate. So you will find that F0 is 0.0256, F1, F2, F3, F4. We have found out all possible values. Now the syntax is if U is less than 0.0256, if U is less than equal to 0.0256, answer will be 0. If U is between 0.0256 and less than equal to 0.1792, answer will be 1. If U is between 0.1792 and less than equal to 0.5248, answer will be 2. Answer will be 3. If it is between 0.8704 and 1, answer will be 4. Clear? So this is what they had written when they were writing this particular form. This is the CDF. We take which point? The higher one. Wherever U lies between, we take finally return xi. This is all we have. There is another section of this chapter called Poisson process. There is a separate video available. We all need to take a look at that. Remember, that is a very important process. It is there in CS1, it is there in CS2, it is there in CM2 as well. So we will see that what we studied in Poisson distribution, Poisson process is kind of closely related to it as well. And there we will also see the relation between a Poisson process and, let's say, a Poisson distribution and an exponential random variable. So that is something I'll need to separately take a look at. It's a very short video, probably 1 hour or so only. So this is all we had in our chapter probability distribution. Any doubts you all have with respect to today's class? Any doubts specifically for today's class? You all could just take this. This might not be there in the material, that you can either equate U as fx or 1 minus fx. And just mention as well, prefer using the first one only. One of you is asking is why is Monte Carlo used? We need to generate samples. Let's say we want to test anything. For example, if I want to calculate the premium, see, unless I sell insurance policies, I won't be able to collect the real data. So I need to generate some sample data. So whenever I need to generate some samples, I use the technique of simulation. So simulation effectively helps us in generating what? A random sample, which can be used to perform any sort of analysis we are looking at. So I guess that's all for the day. Thanks everyone.